Greetings. Today I want to look at derivatives of exponential functions. We're going to start by recalling we have taken the derivative of an exponential function before. We know that the derivative of e to the x is just e to the x. But what about the derivative of a to the x, where our base a is not equal to e? For example, 2 to the x, or 10 to the x, or 37 to the x. We don't have a formula for that yet, but now that we know the chain rule, we can derive a formula for that. So I'm going to show you how this formula is derived, where it comes from. We're going to make it from scratch. And then once we have a formula, we're not going to have to do this derivation again. We're just going to use the formula moving forward. So what we want to do is we want to make an observation. We want to notice that if we have a to the x, this is equal to e to the ln of a to the x power. That might not seem intuitive to you right away, but I want to look at what's inside the parentheses because there is something neat that's going on here. Let's pretend that this was an x instead of an a, just for a moment. If this was an x, then this would be a composition of two functions, where the outer function was e to the x, and the inner function was the natural log of x. Now remember that the natural log of x is defined to be the inverse function of e to the x. So we're taking a composition of inverse functions, and we know that when two functions are inverses and we take their composition, the result is just x, whatever our input value was. And in this case, since our input value is a, then this whole result, this composition of functions evaluated at a, is just going to be a itself. So this whole thing is really just a to the x power. It's a much more creative way of writing a to the x power, but it is still equal to a to the x power. So we've written this in a slightly different way, and I'm going to do one more thing. We know that when we have something raised to a power, and that's raised to another power, we can basically multiply those two powers. So this is the same as e to the ln of a times x. And when we write this like this, we can see that we've got the chain rule. If we want to differentiate this, this is a composition of functions. The outer function is e to the x, e to the u, and the inner function, that u, is ln of a times x. So once we've written it like this, we can take the derivative. So if we want the derivative of our original function, a to the x, that's going to be the same as the derivative of this new function. It's just another way of writing a to the x. So this is going to be e to the ln of a times x. And we can use the chain rule when we're taking this derivative. The outer function here is e to the u, and the derivative of e to the u is e to the u. So we've got e to the ln of a times x. And we've got to multiply that by the derivative of the inner function. Now, ln of a is just a constant, and the derivative of a constant times x is just that constant. So this is going to be times ln of a. Now, once we've done that, we still have this e to the ln of a times x, but we saw that that was just a creative way of writing a to the x. So I'm going to change that back to a to the x. So this is going to be a to the x times ln of a. And this is our derivative of a to the x. When we differentiated e to the x, we just got e to the x as a result. If we're going to differentiate a to the x, we're going to have a to the x times ln of a, which is just a constant factor that pops out. So our rule here is going to be, if we want to take the derivative of a to the x power, the result is just going to be a to the x power times ln of whatever that base is. And so this is a new rule that we can use to differentiate functions that are exponential functions, but where the base is not e. All right, let's do a few rapid fire ones just to get some practice. Let's differentiate y equals 5 to the x power. Well, this is something in the form a to the x. It's just a is 5. And so the derivative is going to be a to the x times ln of a. So in this case, that's 5 to the x times ln of 5. Now, we usually leave our answer just like this, but if we want to have an idea of what this is approximately equal to, because not everyone knows what ln of 5 is, if we use a calculator, we can get an approximation. This is approximately equal to 1.6 times 5 to the x power. Now, we usually don't need decimal approximations, especially when we're dealing with functions. So we're going to want to put the exact answer in WebAssign if you're solving a homework problem or whatnot. But I want to show you this simply because this ln of a, which is approximately 1.6 here, it's just a constant that's getting multiplied by the function. And we know that if we multiply a function by a constant, that changes the graph by a vertical stretch or shrink. So effectively, when we have our function y equals 5 to the x, its derivative is just a vertical stretch of the function itself. All right, let's do one more quick one. Let's look at y equals 17 to the x power. If we want the derivative of that, again, this is a to the x. The derivative is a to the x ln of a, so that's going to be 17 to the x times ln of 17. I've got just a few example problems for this section. A couple of them are going to be straightforward like this, and then a couple of them are going to involve something that's a little bit more complicated where we're going to need to use at least one more rule. So there's going to be a couple of steps, not just one step. So take a look at those videos to get a little bit more of a variety of practice than these basic ones.